Good morning, and welcome to Friday, April 17th. This is AP Statistics. We've already gone over how to do the goodness of fit test for chi-square analysis, and now we're going to move on to the other varieties. Chi-square testing can be done in multiple ways. The goodness of fit test is when there is either one row with multiple categories or one column with multiple categories. So it's really only looking at the distribution of a single variable. For instance, we did M&M color distribution. So on the variable of color, we saw the breakdown for all the 6 colors that they had identified. Same thing with the Fruit Loops problem. So what do you do when it's more than one variable we're analyzing? For instance, is there an association between a person's political party and a person's income class or some such example? Those are better done with chi-square tests of either independence or, the other variety, homogeneity. There's a distinct reason to use one versus the other. However, the approach is practically identical for those two varieties. Today we're going to focus on independence testing. Here's trying to make it real simple. If I take one random sample from a population of interest, I could break it down by any number of different ways to see if there is an association between one variable and another. For instance, if I took 1,000 people from the general population of your hometown and I then sorted the data by their political affiliation and their income class, that would be a test of independence to see if there is an association between those two variables. However, if I took separate samples of Republicans and Democrats and, let's just say, other, okay? And I wanted to see if within each sampling there was a certain breakdown of income class. So in the Republicans, we have X percent in low income, Y percent in middle income, Z percent in high income. And I do the same thing for the Democrats, the low income percent, the middle income percent, the high income percent, and then the others, low, middle, and high. I'll still have a matrix of data that compares two or more variables. In this case, 2. We have the political party is one variable, and income class is the other variable. Don't think that the individual varieties of political affiliation or the variety of income standing is a variable. It's not. It's a level or a factor of the variables that we're analyzing. If I did that, then I'd be looking for whether the distribution of income is equivalent regardless of the political affiliation. So is the breakdown of income class similar between Republicans or Democrats or the others? That's homogeneity testing. We're looking for sameness. That's what homogeneity is. The key difference here, other than one sample versus 2 samples, is in the statements we're going to write, the null and the alternate statement. Remember the words I just used? Is there an association between the variables? We use that for the independence testing, and that's going to be the words we use for independence testing. But for the homogeneity, I said, is the distribution of X variable equivalent regardless of Y variable? That's the wording we're going to use for homogeneity. One thing at a time. Today, independence testing. So what we're going to do here is just a simple example to make it clear, all right? Now, part of it, I'm just going to say, I'm not going to write everything down. But we are going to take a simple random sample of 100 people from, let's just say, the high school. One sample of 100 people from the population of the high school. Of them, 42 are boys and 58 are girls. Of the boys, 26 wear jeans, 16 don't. Of the girls, 38 wear jeans and 20 don't. is there an association between gender and gene preference? Test at the 5% alpha level. We have our question. I'm going to summarize my information here, all right? I have boys and I have girls. I have those who wear jeans and those who don't wear jeans, okay? So jeans and, let's just say, don't. I'm going to make a small matrix of the data that I just described. I said that there were 42 boys. I also need a total row and total column. There were 42 boys. Of them, 26 wear jeans and 16 don't. I also said there were 58 girls. Of them, 38 wear jeans and 20 don't. They don't have to have the same number of boys and girls. It's not an issue of that being a problem. For the totals, I again said that there were 100 people, and of course 42 and 58 does add to 100. There's 64 people that liked jeans and 36 that don't. Remember again, the question is not, do people like jeans better than not wearing jeans? That's not the question. The question is there an association between gender and gene preference? Well, since we're talking about the statements, might as well write the statements. My null statement is that there is no association. For independence testing like this, it's pretty much always, there's no association between, and I'm going to say gender and genes. Okay. What do you think that makes the alternate hypothesis? Simply that there is an association. Okay. Between gender and genes. If there turns out to be an association, we can say what that is. For instance, looks like boys like jeans more than girls, or vice versa, but that's only if there happens to be an association proven. To prove an association is to reject the null that there's no association. We're looking for a low p-value to do that. Lower than 5%, because I said our alpha is going to be 5%. All right, so there have to be conditions here. There's one sample taken, so it's conditions on that single sample. What are my conditions? Well, they're the same as they were before. Is it an SRS? Yes, I said we take an SRS. Does the 10% rule apply? Again, that means, are we sampling no more than 10% of our population? Well, I said my population was high school students, so there needs to be at least 1,000 high school students, either in our high school or in any high school, really. It's not a problem. And lastly, are all expected counts at least 5? Well, you don't know that yet because we don't have the expected counts. So how do we find them? Because that is where we have to go next in order to make sure that we can move forward. Unlike with goodness of fit testing, where the expected count can be either given to you as an expected breakdown, or everything is the same, so we just have the same number, we don't do that here. To find expected, here's what we do. For each one of these cell references, we talk about Microsoft Excel, rows and columns. In this matrix, there's actually 4 cell values. We don't count the totals as cell values. So there's 4 cell values here. To find the expected count of boys who wear jeans, it is the row total times the column total divided by the table total. That's the formula you're going to use to find the expected counts. Now, to make it simple, we're going to show one calculation. You do not have to show all 4 of them. So I'm going to say the expected count for, and take a look at the notation. It's basically spreadsheet notation. In the parentheses, it's row, comma, then column. So row 1, column 1. Row 1, column 1 is boys who wear jeans. So the row total for boys who wear jeans is 42, and the column total for boys who wear jeans is 64, divided by the table total was 100, and I get a value of 26.88. I'm going to do an ellipsis over here, dot, dot, dot. Why do I do that? Because I'm showing that we will continue to do this for the remaining cells, but I'm not going to show it on paper. So here's my expected matrix. By the way, this is my, I'll write it in a second, but that's the observation. These are the expectations. I'm not going to write the J and the don't because they're still lined up. So I have 26.88 here. To find the next one, to find the expected count for boys who don't wear jeans, it's going to be row total 42 times column total 36 divided by table total 100, and that's 15.12. To find girls who wear jeans, it's going to be row total 58 times column total 64 over 100, that's 37.12. And finally, girls who don't wear jeans, row total 58, column total 36 divided by 100 is 20.88. Okay, now I have my expectations. Okay, just going to write down in a different color, if I can pick it up. These are my observations. It's what we see. These are my expectations. It's what we plan to see. If, again, there's no association between gender and jeans. Now, this worked out kind of strangely because the next thing I'm going to show you actually has a common value throughout all the cells, and that's not usually what happens, but it's just the luck of the draw. We have to find our chi-square total. So before I erase what I have to make room, I'm also going to fill in the last condition. Did we actually meet our condition for all expected counts being at least 5? Well, my lowest expected count is 15.12, so everything's more than or equal to 15.12, and that does finish off my conditions before I move forward. We always have to make sure that that works too. If we didn't expect at least 5, based on the numbers, we didn't sample enough and we can't really use these procedures. All right, I've got my observations, I've got my expectations. I'm going to erase this side of my board. Of course, you're not. So you're still going to have the statements and the conditions. I'm going to erase mine because I want to show you how to finish this process and find the chi-square value for each one. Now again, the chi-square value is how different it is from what we expect. So I'm going to make my chi-square matrix for boys and girls who wear jeans and don't. It's going to be 4 numbers I have to find. We're going to find each one of the chi-square values the same as we did for goodness of fit. Observed minus expected squared divided by expected. So I'm going to show you one calculation. So the chi-square value for row 1, column 1, what's going to go right there, is the observation minus the expectation squared divided by the expectation. So 26 minus 26.88 squared divided by 26.88. It's a very small chi-square value because it's really, really, really close to what we expected to see. It's only 0.88 away from what you expected to see. And that's a chi-square value of 0.0288 dot, 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 because we're going to keep doing this for each one of those references. Yes, there is a shortcut I'll show you next time. 0.0288 goes there. If you keep doing that, observed minus expected squared divided by expected, observed minus expected squared divided by expected, and observed minus expected squared divided by expected, you'll find all 4 chi-square cell references. The commonality I mentioned before, 0.88 is pretty much universal to all these values. It's not always like that. That's just a luck of the draw. So here's what you'd fill in. The girls who wear jeans, 0.0209. Boys who don't, 0.0512. Girls who don't, 0.0371. As you might notice here, those are all really super small chi-square numbers. We've been told that the further it is away from 0, the more unusual it is and the more evidence we have to reject the null. These are really, really small chi-square values, which means the null is probably a very safe assumption. But let's finish it. My chi-square total is the sum of those four numbers. And like I said, it's real small. It's 0.138. My degrees of freedom. Okay, here's another difference between this testing and goodness of fit testing. It's not the categories minus 1. It's actually a little different. It's the rows minus 1 times the columns minus 1. You see how we had these four values? There are 2 rows and 2 columns. Well, rows minus 1 is 1, and columns minus 1 is also 1. So this is actually a 1 degree of freedom matrix. It's a very, very low degree of freedom because it's a very small matrix. And then we're going to do chi-square CDF again from our chi-square total of 0.138 to an infinite bound with 1 degree of freedom. Finally gets us our p-value, which is 0.7103. I'll talk through the rest. 0.7103 is a huge p-value. It's obviously more than alpha, which was 5%. It's more than any alpha would be. So this tells us that we are absolutely not going to reject the null. Our evidence was not even close to statistically significant of there being any association between the gender of a person and whether or not they choose genes. Okay? We basically just proved that there's no association between the two. We proved independence. The choice of genes does not depend on gender. There was no clear association. Tomorrow we'll move on to homogeneity testing, and I'll show you the 2 calculator shortcuts that exist to run this procedure. Have a great day.